One really interesting topic that's related to thermochemistry that you will find in various chapters depending on which textbook you're referencing. So you'll need to make use of your table of contents and appendix to find it. So lattice energy. The formation of ionic compounds is very exothermic. We'll use this in later sections to look at things like how much heat they give off and is maybe absorbed by the water solution that they're being dissolved in. Formation of ionic compounds. And I'm going to give you some values, but it's very exothermic. So for example, if we're making sodium chloride, so it's solid sodium, and we have not really done fractions in our reactions so far, but we write it so that it forms exactly 1 mole of sodium chloride. So we only need half of that Cl2 to make NaCl solid. The enthalpy of formation, the standard enthalpy of formation for this is negative 411 kilojoules per mole. That's pretty exothermic. So something that we like to do is try to figure out, well, we did this with kinetics, a mechanism. So like, what are the steps that would get us to sodium chloride? And so you might think of it as an electron transfer, right? So sodium gives up 1 electron, chlorine accepts an electron, and then they're associated with each other because of that. Now, if we do that for sodium chloride, so if we treat as an electron transfer, we can look up values that will help us figure out what that might look like. So sodium giving up an electron, well, that's the first ionization energy of sodium. And this is a positive value, 496 kilojoules per mole. And for chlorine, we want to put an electron on there. That's the electron affinity, the first one at least. This is negative 349 kilojoules per mole. And if we just add those together, right, so think of Hess's law. So overall, add them together, we get, plus 147 kilojoules per mole. This is not a match. So something else is happening in our ionic compound that is making its formation very exothermic. And the thing that's in there that we don't yet know how to account for, but we are going to talk about it, is something called lattice energy. So this is the energy associated with the formation of crystalline lattice. Of alternating cations and anions. So a long, long time ago, we brought up the idea, and so a long, long time ago, sometime in first semester, we brought up the idea that ionic compounds don't exist in sort of these discrete molecule-sized things, right? So if you're sodium 1+, you have kind of a positive charge that can attract negative charge in 360-degree space. So, a bunch of Cl's will be attracted to the sodium. And I'm not going to have the right number here because I'll run out of space, but that's okay. And it's in 3D space. But then the chlorines will all attract sodiums. around them in 3D space. And what you end up with is just Na connected to Cl, essentially. It should be a Cl. And every Cl is connected to an Na. But it's all in this crystalline lattice, and it just keeps going out in this really extended structure. And so this is so favorable, you get a lot of energy out from it. So we need a way to figure out what that energy value might be. And so what we do is we set up something called a Born-Haber cycle, which is also the name of the reaction that has come up a couple of times as we're doing equilibrium. And this is a hypothetical series of steps that applies Hess's law to find the lattice energy. So if we were trying to form NaCl solid, we are going to make it from its elements in their standard states, so Na solid and Cl2 gas. And we do that because if we look up an enthalpy of formation for sodium chloride, we'll get a value. And so we can use the definition of enthalpy of formation and some other numbers, kind of like the ionization energy and electron affinity that we already looked at, to put together what are the steps that we really have to go through, and then what's missing. That missing piece is the lattice energy. So to get sodium chloride solid from constituent elements in their standard states, you can have these steps in any order. So if you thought of a different step to go earlier, that's totally fine. I know that I need to turn sodium into a sodium 1+, and I need to use the ionization energy for this. But ionization energies are only for atoms in the gaseous state. So I can use sodium as a gas, turning into sodium plus and an electron, and use the ionization energy value for this step. But I also have to have a step where I take sodium solid and turn it into a gas first, so that I can use that gas to turn it into an ion. That means that if I want to look at the electron affinity and use the electron affinity to get chlorine to turn into, right, add an electron to it to turn into Cl minus, and use the electron affinity, well, Cl2 is already a gas, but it's Cl2. So I need my 1/2 of Cl2 gas to turn into just Cl gas. All right, if I do these steps, what have I gotten? I've gotten to sodium plus, I've gotten to Cl minus, which is a gas. The only thing left is for my Na plus gas and Cl minus gas to come together to make the NaCl solid. And if I were to take these steps as they are and add them up, my overall reaction, we'll just call it 6, is Na solid plus 1/2 of a Cl2 gas turning into NaCl solid. And this is the value that's known, right? This is what we were just talking about. This is the delta H formation standard for solid sodium chloride. We know that step 4 was an electron affinity. We know that step 2 was an ionization energy. It turns out that step 1, you could look up, it's an enthalpy of atomization. We could just look up how much energy it takes to turn the solid into a gas. This chlorine, it's just breaking the bond. We can actually look up something called the bond energy, and we're going to look at in the video right after this how we can also use bond energies. It's this step that's the question mark, and it's this step that represents the lattice energy for sodium chloride. Now, I didn't write it down, but I mentioned Hess's law. Well, if I add reactions 1 through 5, right, 1 plus 2 plus 3 plus 4 plus 5 equaled reaction 6. So delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H5 equals delta H6, and we know 6, and we know 1 through 4, right? Those are numerical values that we can plug in, and we can solve for the lattice energy value. So we use the Born-Haber cycle to get a numerical value for the lattice energy that helps us explain why the formation of these ionic compounds is so exothermic. So there are some trends that we can look at. So one of the trends that we can look at is lattice energy and ion size. So for some metal chloride, and we're going to look at lithium chloride, sodium chloride, potassium, and cesium. So hopefully you have access to a periodic table. You can see we're just going down a column here. The lattice energy in kilojoules per mole is negative 834 for lithium, negative 788 for sodium, negative 701, and then negative 657. So the only thing that's changing is the metal ion. And as we go from top to bottom in this list, the metal is increasing in size. Okay, so the metal increases in size and it's less exothermic. You can kind of use that as a proxy to say it's not as happy to form this extended lattice, right? It's not doing it and giving off as much energy as the metal gets bigger. Well, part of that, we're going to bring back this equation that you love so dearly, you've probably forgotten about it, Coulomb's law. So the energy of that interaction is 1 over 4 pi epsilon naught Q1 Q2 over R squared. So as the metal gets bigger, the ions get further apart. So as that radius increases, the energy of the interaction gets smaller in magnitude. Okay, so that's lattice energy and ion size. Ion charge, which it's also in Coulomb's law, right? This top part right here. That you will see a trend in as well. So for ion charge, and just looking at Coulomb's law, you can kind of start to predict what this is going to look like. So if my charges get bigger, my energy of interaction should get bigger. So for some compounds, I'm going to give you lattice energy, still in kilojoules per mole. And we're going to compare sodium fluoride, so a 1 plus and a 1 minus. We're going to compare it to calcium oxide, so a 2 plus and a 2 minus. The sodium fluoride is negative 910 kilojoules per mole. The calcium oxide, which we're predicting should be bigger, is significantly bigger. It's negative 3,414. So this is all, right? All we've done is increase essentially Q1 and Q2 because we increased the cation and the anion charge. So it's making that energy of interaction much bigger. So you're getting a lot more heat off when you put together an ionic compound that has higher charges.